Hi everyone, this is going to be the first video of a series I am creating on basic Riemannian geometry. This is aimed to support a class I am teaching, and I will assume some familiarity with the theory of smooth manifolds. I will not cover the prerequisites in detail, but this video should serve as an overview of what I will assume for this course. Later in the spring I plan to create another course that covers this material in detail. In this course, I will try to follow the content of the books by Manfredo do Carmo and John M. Lee. The first one avoids the use of tensors, and I will try to stick to that philosophy, but at the end of each section I will try to give a perspective of the corresponding topic using the terminology of tensors. My current plan is to cover these topics: Riemannian metrics and Riemannian manifolds, where we will go over multiple examples; connections, covering derivatives and parallel transport, where we will also cover how to construct nice connections on Riemannian manifolds; geodesics, where we will show their existence and many basic properties; and curvature, where we will go over the main properties of the curvature tensor and also what are the geometric interpretations of the sectional, Ricci, and scalar curvatures. I have not decided exactly what to cover after that, but once we make a decision, I will put the links in the description of this video. The topics that we will very briefly review in this video are smooth manifolds, smooth functions between manifolds, tangent vectors and the tangent bundle, vector fields and manifolds, flows of vector fields and manifolds, and bump functions and partitions of unity. This material can be studied, for example, in the books by Lee, Boothby, or two I put in the description. If you are watching this after spring 2026, then hopefully you already have a video course on this material. Before we start, I should say that for this course, the words smooth and differentiable will be synonyms, and they will always mean infinity. Now we can start reviewing the material. The first thing we need is smooth manifolds. A smooth manifold is a second countable Hausdorff topological space where we can do differential and integral calculus. This means that there is a family of pairs ui phi I where the ui's are open sets that cover our manifold, and the phi i's are homeomorphisms between the sets ui and an open set in Rn, with the property that whenever two of the ui's intersect, the map phi j composed with phi I inverse is a diffeomorphism between two open sets in Rn. The pairs ui phi I will be called charts. We will also call a chart any other pair u phi where u is an open set in M and phi is a homeomorphism between u and an open set in Rn, with the property that it is compatible with the other charts, meaning that if u intersects one of the ui's, then the change of coordinates is again a diffeomorphism. The main feature of working with a chart is that it provides coordinates in a region of the manifold, which we call local coordinates. These coordinates are what allow us to use all the tools from differential calculus. When we have a continuous function from a manifold to Rm, we say that f is smooth if whenever we take a chart u phi, the composition f phi inverse is smooth. We will denote by infinity of M the vector space of all smooth functions from M to R. More generally, when we have a continuous function f from one manifold M to another manifold N, we say that f is smooth if for any chart u phi of M and any chart v psi of N, the composition psi composed with f composed with phi inverse is smooth in the open set where it is defined. We say that f is a diffeomorphism if it is a homeomorphism and both f and f inverse are smooth. Given a smooth manifold M and a point P in M, a derivation at P is a linear function L from infinity of M to R that satisfies the Leibniz property at P, meaning that if we evaluate L at a product fg, then the result is L of f times g at P plus f at P times L of g. The set of derivations at P forms a vector space that we denote by TPM. This vector space is very closely related to the set of curves passing through P. When we have a smooth curve gamma passing through P at time 0, we can define a derivation associated to it called L gamma. What this derivation does is it takes a function f and composes it with gamma, making it a smooth function defined in a real interval. Now it makes sense to take the derivative at 0. This derivative at 0 is how we define L gamma applied to f. Now we say that two curves gamma 1 and gamma 2 are equivalent if their associated derivations are the same, meaning L gamma 1 equals L gamma 2. It turns out that all derivations at P have this form, so the map that sends gamma to L gamma gives a natural bijection between the set of equivalence classes of curves at P and the set of derivations at P. Intuitively, two curves are equivalent if they have the same direction. More specifically, if we have two curves in Rn passing through the same point at time 0, then they are equivalent if and only if their velocities agree at time 0. To see this, remember that by the chain rule, the derivative of a smooth function along a curve is the dot product between the gradient of f and the velocity of the curve. This means that we can recover the derivation from the velocity and vice versa. Because of this, when gamma is a curve in a manifold, we denote its equivalence class by gamma prime of 0. Following this approach, TPM is called the tangent space to M at P, and its elements are called the tangent vectors to M at P. Once we know that each derivation corresponds to a velocity, it shouldn't be too surprising that the dimension of TPM equals the dimension of the manifold. Moreover, when we work on local coordinates, we can give an explicit basis of this vector space. This is because local coordinates provide a meaningful way to take partial derivative with respect to the first variable, partial derivative with respect to the second variable, and so on. Now, any derivation at P is a linear combination of the partial derivatives in the coordinate directions, so these form a basis of TPM. When we consider the union of all the tangent spaces to M at all points, we get what we call the tangent bundle. It is the set of all tangent vectors to M. This set will have a nice smooth manifold structure, but for now it is just a set of vectors from different vector spaces. Now back to smooth functions. When we have a smooth function f from M to N, then for any P in M, there is an induced linear function dpf from TPM to TFPN. How? We start with the derivation L in TPM. Then notice that for any smooth function h in C∞ of n, the composition hf is in C∞ of m, so we can apply L to it. This very simple algebraic formula has a very geometric interpretation. If L is the derivation associated to a curve gamma, then dfL is the derivation associated to the curve f composed with gamma. When we consider all the points at the same time, we denote the induced function simply by df, and because of its functorial properties, we sometimes denote it by f star instead. Now some terminology. When dpf is injective for all p, we say that f is an immersion. And when dpf is surjective for all p, we say that f is a submersion. When dpf is surjective at all points in the preimage of a given point q, the point q is called a regular value of the function f. Given a smooth manifold M and a subset S, we say that S is a k-dimensional submanifold of M if for any point P in S there is a chart U phi around P such that the image of S is precisely the intersection of phi of U with Rk. This means that S is essentially a slice of M. Smooth functions provide many submanifolds, because by the implicit function theorem, the preimage of any regular value is a submanifold. A smooth vector field on a manifold M is a function x from M to its tangent bundle that assigns to each point P a vector tangent to M at P, and with the additional property that for any smooth function f, the function xf, defined pointwise as x of p applied to f, is a smooth function. The function xf should be understood as the derivative of f in the direction of x. For example, if x is the function that assigns the vector 1, 0 to each point in R2, then for any smooth function f, xf is the partial derivative of f with respect to x. The set of smooth vector fields is a vector space, because we can add and rescale vector fields. We denote this space of vector fields with this symbol. We also notice that this space is a C∞ of M module, because we can always rescale a vector field by a smooth function and it remains smooth. On a smooth manifold M, a global derivation is a linear function x from C∞ of M to itself that satisfies the Leibniz property, That is, x of fg is x of f times g plus f times x of g. Just like pointwise derivations come from curves, global derivations come from vector fields. For any vector field x, by definition there is a linear function that assigns to a smooth function f the function xf. It is not hard to compute that this is a derivation, and it turns out that all global derivations arise this way, so we can identify the space of global derivations with the space of vector fields. Finally, if we have a smooth function f between manifolds M and N and vector fields x and y on M and N, we say that x and y are f-related if for any point P in M, dpf applied to xp equals y of fp. This means that if we push the vector field x via f, we get y. For example, if f denotes the polar change of coordinates, the vector fields e1 and e2 are f-related to the radial vector field and the rotational vector field, respectively. Given two vector fields x and y, we can compute whether they commute or not. And if not, how far are they from commuting? This is done by thinking of x and y as global derivations. We take the function from C-infinity of m to itself that takes a function f and returns the second derivative of f, first in the direction of y and then in the direction of x, minus the second derivative of f, first in the direction of x and then in the direction of y. This is again a global derivation, so it corresponds to a third vector field that we call the Lie bracket of x and y. The Lie bracket is antisymmetric, meaning that if we flip x and y, we get a minus sign. It also depends linearly on both x and y, and if we rescale x by a function f, we get f times the bracket of x and y minus x rescaled by yf. These properties can be verified algebraically without doing any geometry. When we are working in local coordinates, we know from basic calculus that partial derivatives commute, so the Lie bracket of the coordinate vector fields is 0. Also, it turns out that the bracket xy can be thought of as the derivative of y in the direction of x. To make this idea concrete, we need to first talk about flows of vector fields. If we have a vector field and a manifold, for any point P, there is an open interval IP around 0 and a curve gamma P passing through P at time 0 with the property that its velocity at each time is given by the value of x at that point. Moreover, this curve is unique and maximal in the sense that any other curve with those properties is actually a restriction of gamma P. This means that gamma P is the only curve that starts at P and moves in the direction of the vector field x. Curves that satisfy these properties are usually called flow lines of x with initial condition P. We can also consider multiple trajectories at the same time. For any point P in M, there is a region U, a positive epsilon, and a smooth function phi from U times minus epsilon epsilon to M, with the property that phi of x0 is x for all x, and the derivative of phi with respect to time at xt is precisely the value of the vector field at phi of xt. This function phi is called the flow of the vector field x. In general, both epsilon and the set u depend on x, but in the case when M is compact, u can be taken to be M and epsilon to be infinity regardless of x. Now, in the language of flows, we can give another interpretation of the Lie bracket. If we have two vector fields x and y, a point P, and the flow of x around P, then we can use this flow to shift the vector field y along the flow lines of x. It turns out that the infinitesimal rate of change of y at P coincides with the Lie bracket between x and y at P. F-related vector fields behave well with respect to flow lines and Lie brackets. If we have a smooth function f from M to N and two vector fields x and y that are f-related, then for any point P in M and any flow line gamma with initial condition P, the composition f composed with gamma is going to be a flow line of y with initial condition f of P. Also, if we have two pairs of vector fields x1, x2 and y1, y2 that are f-related, then their Lie brackets are going to be f-related as well. For a continuous function f from a manifold to R, its support is defined as the closure of the set where f is not 0. an important property of manifolds is the existence of bump functions. If we have a point P and an open set U containing P, no matter how small is U, we can always find a smooth function ρ that is identically 1 near P, but its support is contained in U. A much stronger statement is the existence of partitions of unity. For any open cover of a smooth manifold, there is a collection of non-negative functions that each of them has support contained in one of the open sets, the family of supports is locally finite, and at each point their sum is 1. A collection of functions like this is called a partition of unity subordinated to the given open cover. Partitions of unity are one of the most important tools in differential geometry. The last thing I wanted to mention today is Einstein notation. Whenever a summand has a repeated index, we are summing over that index. For example, if I write xi ai, we actually mean the sum from I equals 1 to n of xi ai. Similarly for xiyj aij, and we will see many more examples in the future. And I think that's it for today. This is the material that we will work with moving forward. I know it was a lot because, well, I tried to put an entire course in a single video. Thanks for watching, and I hope this series of videos help you while learning Riemannian geometry.